Hey guys, it's CS Wave, and today we're going to be doing Leetcode 971 flip binary tree to match preorder traversal. So the problem is, given a binary tree with n nodes, each node has a different value from 1 to n. A node in this binary tree can be flipped by swapping the left child and the right child of that node. Consider the sequence of n values reported by a preorder traversal starting from the root. Call such a sequence of n values the voyage of the tree. Our goal is to flip the least number of nodes in the tree so that the voyage of the tree matches the voyage we are given. And if we could do so, return the list of nodes that we flipped, and if we can't, just return a list with -1 in it. So basically the problem is flip the least amount of nodes to match the preorder sequence, which is called the voyage. And a flip is defined as swapping a node's children. So given that this is preorder traversal, we'd probably use DFS since we could visit like the current node, then call DFS left, visit that, and then once we recurse back up, call DFS right. And kind of just keep track of the index and compare it to the voyage. And if it doesn't match, then we can swap the nodes. If it still doesn't match, then we'll know that this is impossible. So kind of like the roadmap for this problem, I would say, is called DFS, keeping track of the index, comparing it to the voyage. And if the current node does not equal the voyage, then it's impossible. And then if the node dot left doesn't match voyage, we can swap. And yeah, we basically swap and add current node to result list. And yeah, so that's basically it. Some of the edge cases to think of is like if the starting root doesn't match the voyage, we automatically know it's impossible since we can't swap the starting root. And if left is null and right isn't, we also have to account for that. Then we won't be able to, we'll just have to call DFS left and then right and exit if it's null. And also make sure like double swapping doesn't happen, like don't swap once and then swap again later, because that kind of defeats the purpose. And yeah, this problem looks a little difficult because it says the least number of nodes, so it makes you think like, oh, I have to do a bunch of different variations and pick the best one. But in this case, like swapping is binary, it's either you swap or you don't. So you kind of just traverse the tree in preorder and match it with the sequence. If it doesn't match, swap it. If it still doesn't match, it's impossible. So it's pretty like linear in that way. Time complexity O of n since you're visiting each node. Space complexity also O of n since we're going like worst case scenario, you flip every single node. This would be populated with all of the nodes. Yeah, so what we need to keep track of is the index, the list of integers that will return at the end, call it flipped. And I'll just pass the voyage in here too, so we don't have to pass it in the recursive function. So initially I'll just initialize my list, and index equals 0, and then this dot voyage. And then we'll create our DFS function, which is just going to return nothing. It's just going to iterate through, and if we need to swap something, add that to flipped. And if it doesn't match the voyage, then we'll add -1 to the list. We'll first clear it, then add -1. And then at the end, we could see if the first index is -1, that means we hit an impossible route. So if the node is not null, we'll do something. And if it is null, we just exit out. So if our current node dot val does not equal voyage index, I guess ++ I can increment here too, then this is impossible. So this handles the case of the first node not equaling the voyage. And also whenever we flip and then we call DFS, that flip node, we're also checking that. So it would be impossible both ways. So flip.clear. And then we'll return after that. And then in the case where it does match, then we also want to check if we're at the end of the voyage, we also want to exit. If we're not, then we'll check the left of the node. So if the node.left is not null, and the node.left does not equal the voyage index, the next sequence number. So then we want to swap. So we'll say that we're swapping this current node. Flip.add node.val, and then we could flip it without actually modifying the tree just by calling dfs node.right instead of node.left. So this is kind of like pseudo flipping the tree. So we don't actually have to modify anything, but our algorithm thinks that we flipped it since we're calling right when it actually expects left. And if everything's good, we just keep traversing the tree. Swap these. Yeah, and then once we're returned, we'll have our flipped list. So we want to first check if flipped is not empty. So if it's not empty and flipped dot get 0 does not equal -1, or I guess if it does equal -1, then we know it's impossible. So we'll clear it and then add -1. And at the end, we could just return flipped. Since if it worked, it will hold all of our nodes that we flipped, and if it didn't work, we just return a list with -1. So yeah, this handles the case. This handles all the edge cases, O of n time, O of n space. Let's run this now. Oh, what did I do? No.left.val. Whoops. Cool, so the test case works. This would be impossible if it was just 1 and 2, because you can't match the voyage to 1 to 1, 2, since you can't actually flip 1, since it's a root. So I'll try submitting, and it should work. And yeah, it works, 7 milliseconds. So yeah, that's the problem. I thought it was interesting. DFS problem. The description's kind of weird, but it's still an interesting problem. So yeah, that's it. Thanks for watching.